to day two. So here's a quick summary of what happened yesterday. In the first lecture, what we did is to rigorously and with details introduce the following geometric framework. There's a Legendre knot lambda drawn in orange, and that lambda lives in this T infinity of M, the unique attention bundle of M, where M is taken to be the plane throughout the lecture so far. And now you care about that Legendre knot as a knot in a contact 3 manifold. And one way to study it, to understand it better, is to project it down to the zero section. That's this pi of lambda drawn in red. And that projection generically will have two kinds of singularities, either simple cusps or crossings. And one of the theorems that we discussed yesterday, after giving some examples, was that two Legendre knots thought abstractly in the 3 manifold are Legendre isotopic, even only if there exist fronts which are connected by a certain sequence of Rodameister moves. So that was the first thing, kind of a purely contact problem. Now, this T infinity of M as a contact manifold is filled, it's a symplectic filling by T star of M. So the symplectic cotangent bundle of M, in this case R2, does act as a symplectic filling of this contact manifold. And you can ask the question, are there Lagrangians L in blue that bound this lambda in the contact boundary? And you want them to be exact and unobstructed in general, but for instance, exact embedded already assures that. So maybe you start hunting for exact embedded Lagrangians, which can help you distinguish knots lambda. And for a given knot lambda, it can just inform you better about its geometry. And we saw a second kind of tool, which is certain set of moves in the knot diagram in the front that allows you to build some Lagrangian fillings. You remember those surgeries, if you have an unknot, you can make it disappear, you can do that pinch move, and if you have two crossings, you can make it one crossing. So those are ways, constructive ways to build such Lagrangians L, and actually they will suffice for the purpose of this lecture. Does that make sense so far? So that was lecture 1. And then lecture 2 started to answer the question, or try to answer the question, okay, how do I know if two knots are not Legendrian the same? Maybe they're smoothly isotopic, maybe your rotation and TV, your classical invariants are all equal. How can I tell that they're not Legendrian isotopic? And similarly, if I have two Lagrangian fillings, how do I tell? Maybe they're built very differently. Maybe I cannot find a movie of movies between them. How do I tell that those two Lagrangian fillings are not Hamiltonian isotopic, which is the same as exact Lagrangian isotopic? And the key idea was to really think of this front, of this M, and think that what we're going to do is to express these lambdas by studying sheaves on M. And recall, they're pretty mild sheaves. They're built out of things that are kind of constant, like characteristic type functions. K somewhere, 0 outside, so on and so forth. There are all the subtleties, and that's why the lecture took some care of what's closed, what's open, the coorientation. But the idea is that those sheaves on M will connect to lambda via the notion of singular support. So that's what's written over there. Given a lambda, you can name what singular support of a sheaf is and consider the category of all sheaves on M whose singular support is on lambda. That names a category for you, and that category, might or might not be computable, might or might not be an invariant of lambda. In the second lecture today, I'll discuss things about that, about whether it's an invariant. But in the first lecture today, the goal is to compute that category in some sense. And in order to do that, we'll go really down on the fronts and stratification, so on and so forth. But again, the second lecture associated this category sheaves sub lambda of M, which are sheaves on M whose singular support is on lambda. And intuitively, what you want to think is that those sheaves come from Lagrangian fillings, and conversely, a Lagrangian filling, you want to hope, again, second lecture today, that you can make it come from a sheaf sometimes. Does that make sense? Okay, so that's the setup. Okay, so here's the thing. When I was starting to just study invariants that were non-numbers, I started to panic a little bit, because when you're in high school or elementary school, wherever you are, you're told what it means to solve for x. That we're trained for. X has a value 3, maybe x is a quadratic equation, x has 2 values. But then after that, you go into undergrad or something, and your invariants are not numbers, they're not discrete sets, they're maybe polynomials. And then they're no longer polynomials, they're homologies, they're graded abelian groups. And then maybe they're like actually homology rings, so there's the ring structure. And then suddenly they become categories, and there's an adjective in front of the category that makes you kind of allergic to it sometimes. And things kind of keep building up. So what do we mean by compute a category? So, okay, one way to think about a category is that it is the category of modules of representations of something that you understand pretty well. So imagine that your category is of the form R mod, so modules over a ring R that you really like, something like a polynomial ring or an exterior algebra. Then you have the kind of centuries of algebra behind you to say, well, then I can classify the generators of the category into composable representations. It kind of becomes a problem, quote unquote, of linear algebra, right? Like kind of becomes a problem of R module theory. And maybe that ring is not really commutative, as it happens in contact symbolic topology. It's almost never commutative. So now you've got to have good understanding of representation of non-commutative algebras, which is just not there in the literature. We still have a lot to learn about that. But it is somewhat an algebraic problem. So by computing, I don't mean, oh, you make it accessible so that everybody can compute everything. By that, I mean, you translate it into a problem which is either algebraic or it's combinatorial. And then you have to deal with that problem, but that's sort of no longer an issue of algebra and geometry. So you can go literally, and I do that, to a conference on quiver representations or to a conference on like non-commutative representation theory and pose the problem purely in those terms and try to discuss those with experts. So that's what I mean by computing. Present the category in a way that has completely stripped of any contact and symplectic topology, and now it's kind of an algebra problem or a unitarist problem. Not to diminish the value of those fields, like that themselves have to solve this. All right, so a very important thing about sheaf theory and this perspective, which kind of contrasts a lot with all the sort of morphic developments since '85, is that you really stick with M. You don't really think of anything but M, except for this notion of singular support. And you really take this idea that sheaves on M like kind of know everything, and all computation should happen on M themselves, like nothing else but that. As a general analogy, I'm going to start writing soon. As a general analogy, maybe we're all in agreement, or we all kind of have background on finite Morse theory. And we also have background on hatchers, like singular cohomology, simplicial, so on. Essentially, what's happening, vaguely speaking, is what we're doing with sheaf theory is the singular cohomology stuff. Okay? So it's something that can be defined. As defined abstractly, it's effectively impossible to compute. If you ever tell your grad students compute, the singular homology of a torus, they're going to be like, I don't know. The only example hatcher does is a point, and that's it. The rest is like Meyer-Vietteries and all sorts of tricks, right? Note that if you were a Morse theory person and you came into a class and somebody was telling you that you're computing the Morse homology in terms of those infinite chains, it would look kind of crazy. And you would be like, where are my critical points? Where is my function? And the answer would be, it's not there. That's exactly the same with fourth theory. Where are the holomorphic disks? Where are the intersect? They're not there. And it's fine. That is not to say Morse cohomology coincides with singular cohomology. It's just like it's presented with the data of the F in terms of generators that those just don't exist in singular cohomology, or if you wish, they're just infinite families. So the analogy now is if sheaves on M or sheaf sub lambda on M is singular cohomology, what's the first step you do in a Hatcher class or an algebra topology is you say, well, let me prove that this is equal to either simplicial or cellular, something that's much more computable. Obviously, simplicial or cellular, what's hard to prove is that it's invariant. Like simplicial, it's hard to prove it's invariant. It's kind of a pain in the neck. But you show it's equal to singular, so you get all the advantages of the singular, which is really homomorphic invariant, but then all the computational point, right? So today's class is on simplicial cohomology, okay? But from the sheaf viewpoint. So is how do you express that sheaf sub lambda of M in terms of computable things? Not triangulations, but in this case, fronts. So the first thing that I'm going to discuss is how do you go from fronts, which again, kind of play our role of triangulations or combinatorial data to stratification. So both fronts and stratifications play this role of combinatorial data, which is finite, it's something manageable, and it's something we can understand. Okay, so let's give an example here. So the lambda that I'm always going to think, and I'm going to draw lambda, but this is really pi of lambda as a subset of R2, Q1, Q2. Maybe we'll have this shape. Say you take something like that. And you really come into the room and look at this and say, what is this? Is it a node? Is it a front of? No. What it is a drawing in R2. That's all it is. And it has some points that are kind of more special than others. And the idea is that you look at it and you say, this is partitioning R2. So the front can partition R2 in the following way. You can say, I'm going to declare certain sets, let's call them S0. Those are going to be the cusps as a set of points. This is literally as a set of points, and these are the crossings. So this is going to be a point, this is going to be a point, this is going to be a point, this is going to be a point. And those, all of these are considered as independent singleton sets. And now you think about it and you say, well, actually there are the points, but there's also something else, which are exactly the arcs. So I can call S1, the subindex is going to indicate the dimension, arcs between points. And so, for instance, this is a perfectly fine arc. This is another arc. This is another arc that's allowed. Does that make sense? And finally, I have the complement of all these sets, which is now a bunch of connected components. So I have S2, sort of the open sets. So open sets remaining. So for instance, one open set remaining is this one. Another open set remaining would be kind of like that. That will be another one. This will be another one, and then there's the unbounded component outside. So this partitions the plane. So the plane is now partitioned. This is a set theoretic statement. I'm not saying anything topological. The set theoretically, we've presented the plane as a partition of S0, S1, and S2. So this is a set theoretic partition. Now, we're doing topology. Let's not forget that. So we have a notion of what it means to be nearby somebody. So we have a notion of closures, of limits. And in fact, this partition has a nice property, which is it is a stratification. So this construction inputs in general a front in R2. So this is pi of lambda in R2, and outputs a stratification, which I'm going to tell you what it is right now. So a stratification, which I'm going to be calling S, fancy S, sub pi lambda of the plane, often. In this manner. So what is a stratification? A stratification is a slight enhancement of a partition in a topological direction, in the sense that what you're going to ask is that the closure of any stratum is itself made out of other strata. So closure of SI is SI union other strata. So the sets in here are all called strata independently. And so it's union of the other strata. So for instance, let's do an example. If I take this set in here, remember, this would be a set like this one, this arc over here, that will be a set in S1. So that will be an example of a stratum in the one-dimensional strata. So this is one-dimensional strata. Zero-dimensional strata, one-dimensional strata, two-dimensional strata. Strata is the plural of stratum, which is the singular. And if I took the closure of that, the closure of this closure, it's now going to be this guy union these two additional zero-dimensional strata. Does that make sense? So that indeed has the property. In general, for any front, generic front like this one, you're going to exactly have that property. Does that make sense? So now I've told you how, given a front, you really think of it as a set partition, and actually it's slightly better as stratification. And for experts, this has all the good properties you want, like Whitney stratification. It's a really nice stratification. In fact, for knots, you can, except for the outer component, you can assume every component of the stratification is actually contractible, which makes it particularly nice. Are we okay with this viewpoint so far? Okay, so now, where is the sheaf? Where is the singular support? Where is anything? Well, what do we know about this? What we know is that we want the sheaf to have singular support exactly on the Legendrian. So the sheaf, whatever sheaf we're considering for singular support we want to be in the Legendrian, should be such that whenever I consider something in here versus outside, that there might be a change. But what if I take a stratum, say this one in here, I take a point inside of my stratum in here, inside here, or in a black stratum in here, and I move within the stratum? Question. Think carefully, it's an important answer, it's not a hard one. If I move within the strata, in whichever strata I am, if I move within it, am I allowed to change? Am I allowed to have a direction in the singular support of the sheaf if I'm contained within one stratum? It's a binary question, yes or no. So carefully. Okay. So the answer is no, you're not. Because if you were allowed to change the sheaf in the direction within the stratum, that would mean that there's a direction in singular support of the sheaf within the strata, which would mean there's a codirection, which is not the downward codirection, which actually is in the singular support, so that singular support would not be on that. So when viewed from this viewpoint, what you learn is that whatever sheaf you're considering that has singular support on lambda, it ought to be that when restricted to every strata, the sheaf is locally constant. Does that make sense? So now I was hesitating about what to talk about sort of next after this, in the sense that now I could talk for 10 minutes about what locally constant sheaves look like local systems. But what I'm going to do is, I'm not going to do that, okay? Because in this example, they're kind of all trivial because there's no interest in topology. I'm going to rather state a more general theorem that explains how to compute these kind of sheaves. And then at any point today in the group work or in the math Q&A, you want me to talk of the easier case of local systems, which corresponds to the case of the empty Legendrian, I can do that at length, okay? But I also kind of need to get to the main results. So, okay, so what we want now are sheaves. So maybe I'll state that very clearly here. One sheaves, so one F, such that F is locally constant on each stratum. It is not saying much at points, but it is saying something at arcs. It's certainly saying something in open sets. Okay. All right, so now the goal is classify, given a stratification, such as this one, all sheaves that are locally constant with respect to the stratification, meaning they're locally constant in each stratum. Somewhat luckily, this is a very old problem. This actually comes from study of subanalytic sets in algebraic geometry, analytic algebraic geometry, and those sheaves have a name in the literature, and they're called constructible. So when you hear the word constructible, comes from constructible sets, constructible sheaf is a sheaf which is locally constant with respect to a stratification. In our case, we do better. It's not just a stratification, it's this stratification. So one thing we can immediately say purely out of language is the sheaves in SH sub lambda of M are a subcategory of the category of constructible sheaves on M. Better yet, it's a subcategory of the sheaves which are constructible on M with respect to the stratification given by A front. Okay? So now, how do you compute constructible sheaves? So that's, as I said, something that people have thought about for a long time. So this is a theorem. It's called the Exomon. I'm going to give you 25 theorems, some of which came from results from the 70s and the 80s. This is called the exodromy equivalence. And you should think of it, despite the funny name, this is a way to compute constructible sheaves on a space. Translating that from a problem on sheaf theory or homological algebra to a problem in representation theory, quote unquote, linear algebra. Okay? So this is what it says in this specific case. So let, in general, let S be a stratification. I'm going to do this precise case, stratification of R2. And you could either add words like conic or Whitney. Whitney is an example of conic, but you can just think example from a front. And any such guys will be good enough. Then there is an equivalence between these two categories. So the first one is the category of sheaves, which are constructible with respect to the stratification. This is sometimes denoted like that. So I'm going to add words and say things here and there. So this is, just know, those are AKA constructible sheaves. So constructible with respect to M. But again, don't be afraid. With respect to S. Don't be afraid with the word. It just means locally constant on every stratum. So this is a problem in sheaf theory. Now, interestingly enough, the notion of singular support actually allows you to write these in a nicer way as well. So you can think of these as actually being the category of sheaves whose singular support is the conormal of the stratification. Okay, so this. So what I'm saying is this is a notation to mean constructible sheaf with respect to S. This literally is a singular support category. So this is a category that is named with a singular support. But the singular support is not going to be on lambda, it's going to be on lambda plus a bunch of stuff. So singular support on lambda plus extra. And you don't want the extra, you want to get rid of the extra, right? So what is an example of this? So if you're locally constant along this stratification, you're locally constant along the arc. Now, locally constant along the arc says nothing about whether you're locally constant in this direction or not. So if you just say constructible, you may have singular support both in the downward direction and both in the upwards direction. So that's what I'm saying. That's not the lambda we wanted. There's extra directions that are being thrown in, but it's still kind of conceptually neat to say, actually, all this classical theory is an example of singular support. It's just an example of a singular support with lambda being singular sometimes. Okay. Again, another quite striking difference in floor theory, it is really tricky to manage invariants of singular Lagrangians and singular Lagrangians. In sheaf theory, it's like essentially no problem. You can absolutely find them and show their invariant. And that's because this thing doesn't really care as long as you're essentially a subanalytic set. Okay, so this is the sheaf side that we care about. Our category sheaf of lambda is inside of it, but it typically does not coincide with it. This is what we care about. Okay, here comes the punchline. This is equivalent to, so I'm going to first write what this is. Category of functors out of something called the exit path category, S, associated to M, to the coefficient category. So in this case, it's going to be mod K. Recall that if I don't say anything, I always take chain complexes. It's like, okay, so what is this business? So this, you should think of it as informally, all this whole thing, all this whole right-hand side are just representations, broadly understood, modules, representations of this piece. Of this category, exit SM. As an example, if the stratification is empty, this is just, okay, the short answer is, if the stratification is empty, this is just the fundamental Poincare groupoid, which is a generalization of pi 1. So in a very basic case, this is just saying constructible sheaf with respect to the trivial stratification. So people who are locally constant everywhere, those are just representations of pi 1, also known as local systems. There's an infinity enhancement of that, where this is now this Poincare infinity groupoid. And in general, for locally constant sheaves everywhere, so S being equal to M, one big stratum, this would just be chains on the base loop space of M. Does your spidey sense of floor theory start to ring a bit? Oh, the Raphukaya category is equivalent to the chains on the base loop space. This is exactly that. This category, modules over this category, is literally representations of the chains on the base loop space of M. If S is taken trivially, if there's no stuff. Okay? So you see, like, there was never a holomorphic anything. It's like we're doing more theory, now we're getting the same answers, but we're doing it kind of purely in terms of kind of simplicial things, computational or singular. All right. So what is this in general? So in general, this is objects given by points in M. And it has morphisms given by homotopy classes of paths from a lower stratum, from paths that always go up in dimension, that always go up in dimension of stratum. Okay, let me give you an example. So an object in this category, for instance, is this point over here. This is a perfectly nice point. This is another point. What are morphisms between these 2 points? I'm allowed any path that every time that it changes stratum, it goes to a higher dimensional one. So this guy is allowed to do a bit of, oh, I'm liking it here, and then go, and then I'm going this way. It's not allowed to do, I'm going in here, now I cross this red point, because that's the lower dimensional strata, and then go somewhere else. Okay, does that make sense? It's also not allowed to go into this stratum, because then it's going to be forced to cross out of that, and that will be again decreasing. Okay, so what are morphisms from here to here? Well, there's none because you're forced to cross. What are morphisms from here to here? Well, it's homotopy classes of paths from here to here. If there's interesting topology in the stratum, that's what recovers it, such as phi 1. And when you do the infinity version, you recover, in general, change of the basis of space, or change of the path space. Does that make sense so far? Okay, so if you happen to be in a case where the strata are really nice, say they have no topology whatsoever, like this one, say we're going to always ignore the tops, the outer strata, put the sheaf is 0 there. That's kind of for convenience. And given that it's not simply connected, it's particularly convenient. But every other strata here is contractible. So that means that actually the only data in a given stratum is any point, because any other point is isomorphic to it, because there's a path to it and back, right? So in that case, what you have is the data that every stratum gets a point. That's kind of its representative. And now, what is an exit path? Well, because there's no topology happening, an exit path, there's essentially one unique morphism that goes from this point to this point over here. So in our cases, this is going to be a much nicer category. So in the cases, so if phi of lambda has all strata contractible, that's all, which will have, is all contractible strata. What these are just representations of the pose set, which is, I mean, in particular, the partially ordered set given by these things. So this is representations, K-module representations. Of the pose set, partially ordered set, associated to, let's say the front, really it's associated to the stratification of the front. So associated to the stratification as some lambda. Well, let's do an example of that. So what would it look like in the case that I was discussing over there? So we're in here. The stratification is described in that blackboard over there. What is the pose set? I'm going to draw it in red. So the pose set is going to have one element. A pose set means partially ordered set. So first of all, it's a set of elements, and then there's a partial order between two people. Sometimes you can say who's larger than the other one. It's transitive and reflexive. Okay, so we're going to choose one element per stratum. So each of these people are going to have their own element in here. And then there's also going to be the dots, so zero-dimensional stratum. And then there's going to be kind of the big strata, squares. And what is the partial order in this kind of set?
Are you missing 4?
Problem. Thank you. Okay. Well, okay. Not everything, all the strata. Good. So what's the order? The nice relation here is as follows: is that Si is said to be less than Sj if, when you take the closure of Sj, that includes Si. So the closure of Sj includes Si. For instance, if you take this arc over here, as we were doing before, these two people are going to be inside their closure. So these two people are going to be less than that guy. So for instance, these two dots in here are less than this guy, they're less than this guy. Does that make sense? Now, partially ordered sets, then instead of using this equivalence relation, like writing it here, you can just write an arrow. So you can just write an arrow going this way, and there's an arrow between an element and another, even only if this element is less than the other. This is just like a rephrasing of these. So for instance, what are the arrows here? Well, this stratum is in the closure of these and these, so we will have arrows here and here. This guy also in the closure, so there's going to be arrows coming from here. This guy is in the closure of this arc stratum, so it's going to have an arrow here. It's also going to have an arrow here. But we also have an arrow over here, and we also have an arrow going all the way to the outer one. So given any front, you get a pretty elaborate diagram. There's a bunch of points and really a lot of arrows. And what is the representation of that? Oh, now we're in the land of linear algebra. Now you can go back to your undergrad freshman professor and tell them, well, you taught me linear algebra, you should be able to solve that. So what does it look like? It looks like I get to assign any vector space, any k module I want to any red dot, and any green arrow gets a k-linear morphism. So in this case, if you wish, you can think of it as the matrix, it's just a linear map. Does that make sense? So far, no constraint of the dimensions. They could be dimension 3, 17, 8. The maps could be all 0. The maps could be all like, I don't know, surjective. There's no constraint whatsoever. And that captures the richness of this category. Anything like that will have that. Now, the singular supports you're going to get are going to vary widely depending on what kind of maps you have. If you like put zeros everywhere, that's going to have very different singular supports than if you put like some interesting maps somewhere else. Are we good so far?
Sorry.
Yeah.
Maybe you mentioned this, but maybe I forgot. How do you deal with the fact that the outer strata is not convertible?
So we are going to be restricting. Okay, so there's two excerpts. If you were dealing with this general statement, what you would have to do is assign these plus a representation of change on the base loop space, because it's homotopy to S1, that would just mean representation of pi 1. So then you would really have a representation of these plus an automorphism of this vector space. So that's a general statement. In practice, we will often just restrict to the subcategory of sheaf here that have 0 stock outside. And so this will always be forced to have the 0 vector space, so this automorphism is not seen. In real life, papers, this is very important sometimes, especially in the Riemann-Hilbert correspondence. So one of the papers I wrote this year on the Riemann-Hilbert correspondence viewed from the contact viewpoint, these kind of things are really important. So it's not always that you can do that, but in this lecture we'll go to that. But otherwise, we just add the automorphism. Does that make sense? Okay. So before I go and kind of compute stuff, so this is the computable world, the simplicial world, the triangulation. I don't know, this sign doesn't look like a triangulation, but kind of looks like, but points and arrows to the combinatorial. You can tell me, this is sort of an audience question, which is like, do you want me to say a word or two about how this is proven, or you just don't care? I mean, you can just take this as a black box. Okay, Dan says yes. So maybe we'll mention something briefly. Okay, so the first thing to say is that this is nothing but the Galois correspondence, as many things in life. So what do you learn in Hatcher, or out of an algebraic topology course? You tend to learn something of the sort, if I'm trying to understand maps out of the fundamental group, that is going to be equivalent to understanding covering spaces over my space. So you have a space X, covering spaces over X is equivalent, properly understood, categorical equivalent, to morphisms out of the fundamental group. Okay, and you represent the fundamental group as an automorphism of something, and that something is exactly the finder. So you have a covering space with like 3 people, then you're gonna get this into some automorphism group of like 3 elements, representation of 3 elements. Does that make sense? Now, years later, Galois is, dead, like very old. Okay, so years later, Grothendieck and now Lurie have generalized that vastly. And in general, there's a general Galois type principle that says spaces that map to X are in equivalence with spaces out of X. So if you're trying to do some kind of covering like spaces over X, that's the same thing as mapping out of X. Okay? A good example of that is local systems. You can think of local systems as really being locally constant sheaf representation of pi 1, or you could think of them as vector bundles with a flat connection. Vector bundle is something over X. Right? So this is called the Grothendieck construction. If you have to Google that, it's called the straightening and straightening adjunction. So there's names for that. If you read higher algebra, Lurie has set up this very nicely in the infinity categorical setting. But the idea is that you also do that for categories. So given an infinity category, functors out of a category is the same as what's called Grothendieck fibration onto the category. It's kind of some kind of, there's a functor between categories that kind of looks like a fibration. Like every, for instance, the primitive of every object is a category. That would be the functor. Does that make sense so far? Okay, so what do we have on the right-hand side? On the right-hand side, we have something which is maps out of this category. Do we agree? Under this kind of straightening and straightening adjunction, you can think of these as being equivalent to fibrations, the correct term is left-hand fibrations over this category. So those are categories that kind of fiber over this category. One way to think about it, if you have thought about model space and algebraic geometry, is that this guy has some kind of universal family, and under any function you can pull it back. Remember how you get a vector bundle out of representation of something is you just pull back the universal family under the classifying map. So now I have some category. This is equivalent to having some category left kind of fibering over this one. But now you have a vector bundle. You know how to give a sheaf out of a vector bundle. What would you do if you have a sheaf? Sorry, if you have a vector bundle and you want to name a sheaf. You do it sheaf of sections. That's it. That's exactly what you do. So these sheaves that you assign going that way, the inverse of this map, it is literally for any open set U of these, you will assign sections over U. So of that guy. So given such a functor, you think of it as a fibration, and then you take sections, and that's how it connects to sheaves. So I know this might appear very different, but again, keep in mind this sort of theme in math, where maps out of X are the same, appropriately understood, as maps onto X. And then you go to sheaves, because when you get onto something, you can take sections. Is this intuitive enough for the time being? This is never dismiss, your law correspondence class, or whenever you're teaching it to your students, really try to understand. There's a lot of juice there. All right. I'm going to do computations now. Are we happy so far? All right. Okay. So the goal will be to compute this category now locally, and then we'll just patch it together. And for fronts of Legendrian knots, actually, it suffices to study 3 local models, because as you have seen here, the only things that really we need to care about for Legendrian knots are arcs, cusps, and crossings. And if I understand what's happening near an arc, near a cusp, and near a crossing, then I'm done. All right. Now, appreciate that everything I'm doing for Legendrian knots here, it's very computational and friendly. If I had a higher dimensional front, a spatial front with more complicated singularities, you need to work out what that stratification looks like. This poset might look more complicated. And, David Truman, myself, we've worked some examples in higher dimensions, and it's kind of interesting. So Alison here, part of her thesis is working out a pretty interesting stratification in high D to do with cone. So those are still things that we are understanding better. Yeah, Roman.
So in this proof, how to convince yourself that when you start with sheaf and apply this strategy, you get back the same sheaf? I mean, like
why
you start with a sheaf, you get a functor from exit category. Then you apply this machinery, you get back to the solution.
Yeah, so we can talk more carefully about that. I would say I would break that into 2 steps. The first step is understanding that this is an adjunction. That's the first step. And then it's not just it's an ISO, the adjunction themselves gives you the inverse. So I would say first of all, understand why this is an adjunction. And once you've understood that, then try to understand why it's an ISO. But yeah, we can talk about it. The short answer is also it's in Lurie's book, so I can refer you exactly to the page, the higher algebra. But yeah, think of it as an adjunction that happens to be equivalence. More information being an equivalence. Okay, good. Okay, so now local models for this. So local models for this kind of stratifications in front. And now what kind of posets we're going to get. So the first local model here is that of an arc. The second local model is that of a cusp. And the third local model is that of crossing. So here I'm going to draw the local model, and it's going to have 1 stratum here, and then 2 stratum here, up and down. So the poset is going to exactly be this kind of poset. Does that make sense? Okay, so now it's when I hope all of you are paying very close attention to House talk. Have you seen something like that in House talk? Yes. So there's 2 comments here. The first one is, in fact, for these kinds of examples, what you're assigning to each stratum in the representation that we're going to have here associated to a sheaf is literally the stock. So you can think of it as the stock here, the stock there, the stock there. Now, what this map is a map between stocks, but properly understood, what the second map, what either of the maps does, but like this map, for instance, going from here to here, what it's doing it's taking sections over here and restricting them to the bottom. So I'm doing this very carefully because these, you can think of like sections. So this is f of u, and this is like on the entire arc. So these sections on here, and then restrict the sections on, so sections f of, and the tricky thing here is you're restricting the sections on the bottom. So sections on here on the bottom. And why am I saying this is tricky? Because this is the fact is, this is exactly about testing the codirection that goes up. Okay, so a lot of confusion I have learned this, thanks to my students, is that this arrow goes down, but it has nothing to do with the codirection going down or that direction. Rather, when you're testing whether this is in the singular support, this being in the singular support is the thing that compares global sections here with global sections on the back of this, right? Remember the Microsoft definition yesterday? So this map being an ISO or not is telling you whether this direction is in the singular support. So please, it's just what map is, but this is how it works. The map that goes down is actually the thing that's testing whether the singular direction up is an ISO. Are we okay with that? Seems stupid, but please, when you make this mistake, because you're going to make this mistake, just correct yourself. Okay. And if you don't make this mistake, it's good for you. Okay. So this is the poset that's happening in here. So that would be the poset in there. Here, the poset is slightly more elaborate. It's going to have this one-dimensional strata, two arcs, zero-dimensional strata, and then it's going to have two-dimensional strata. And the arcs are going to be, well, both arcs map to the big one. And then the point, well, it's in the closure of everybody else. So the point is going to map to absolutely every strata. Does that make sense? So this is how the poset looks like. And again, as we described in here, this mapping here going from here to here is capturing the singular support in that direction. So this singular support direction is this map. Does that make sense? Now, this guy has many directions, inside, there, and there. And of course, that captures different directions of the singular support. And they're essentially being captured is the singular support within the stratum itself, within this stratum, or kind of outer. This one captures this one, and this map captures the other. Okay, so always think the other way around. Okay, so the poset is slightly more elaborate there, and then finally the poset that's sort of automatic, it's this one. So this one size. That's regular somewhere. So there's the top strata here, the arc strata here, and now the arrows are going to go from the last stratum to this one, so arrows this way. And then there's arrows from this guy to any of these points, so it's going to be an arrow this way, this way, this way, this way. Then there's going to be two arrows going this way, this way, this way. Does that make sense? So hopefully I haven't forgotten any arrow. Okay, so now what are representations of any of these people? Well, representations of these is really easy. For instance, I could say I take the vector space K here, the vector space 0 here, and the vector space like 0 there, for instance. If I do this choice, then this map is going to be an isomorphism, whereas this map is not going to be an isomorphism. So what will be the singular support of this constructible sheaf be? So this is not an iso, so the singular support is up. This is an iso, so there's nothing in the singular support. So the singular support of this will literally be the Legendrian with kind of the hairs going. If you want the Legendrian with the hairs going down, then you would ask this guy to be an isomorphism, and this guy not to be an isomorphism. For instance, you could have something like K, K0, something like that. That would have singular support. Now going.
That's assuming the upward map is an isomorphism.
Sorry, yeah, this is an extra piece of data.
Yeah.
This is very important, and it's natural if you're confused at the beginning, but when whole how talk and everything, sheaves are not determined by their stocks. Okay, so don't think about just stocks. You really need the maps, and most of the juice information of a sheaf is on the maps. So as John very correctly points out, saying K and K doesn't tell you enough. You need to say this is an isomorphism. If I chose a zero map here, the singular support would still be in both directions. So, if this, so, okay, there's two examples here, example I and example II. Let's see what else I'm saying. If this map is an isomorphism, then the bottom direction is not in the singular support. If this map from 0 to K is not an isomorphism, which will never be, then the upwards direction is in the singular support. So on the left-hand side example, the upward direction will be the singular support. In this example, if this map, I see what you mean. Yeah. So it's this map. Okay, so we could have chosen that. If this map is an isomorphism, then this is not in singular support, but this not being an isomorphism tells you. Good. You're well trained. She's self-trained. Okay, so this is particularly simple diagram. Okay. When we're now doing representations here, so representations, again, assign a vector space at every point and map between them. The representations assign a vector space, assign K module to each point, and linear to arrows. You can think of it just as the poset is a category with objects being its set and the maps being this, and this is literally a functor between the poset as a category into the category vector spaces. But you need an extra condition. I'm going to write this in red, such that all diagrams commute, such that all diagrams that can commute do commute. Right? So for instance, here I could assign a vector space to this guy over here, and a vector space to this guy, and a vector space to this guy. Then I have a choice of this map over here, and I have a choice of this map over here. What I'm saying is you do not actually have a choice of this map, because you're forced to have this little triangle commute over there. And squares, triangle, whatever commutative thing that you can draw in there, that should commute. So that's the first time where you're like, well, I have a lot of arrows, but I don't need all of them. Like, I don't need this arrow because it can be recovered from here or from here. I don't need this arrow either because it can be recovered from here or from here. Does that make sense? So that's the first time where you can simplify a bit the poset and not care about like all the arrows all the way. Similar considerations apply here. I don't really need this arrow over here because it's considered this arrow plus this arrow. So the fact that this diagram commutes, that tells me I don't really care. For instance. Okay. So very interesting thing to begin with. When you start talking to Quiver people, read the Quiver literature. These, when they talk about Quiver representations, this is usually not a condition. Well, actually, it's never a condition. So you would say, oh, this is now, there's literature on Quiver representations. These quivers surely are studied. I'm going to represent it. That's not what you want. You want quivers with these diagrams commute. So in the literature, this is a remark, in the literature, calls this quivers with relations. So if that's what you're interested about, quivers with so representation varieties and blah, blah, blah of quivers with relations. And the relation is compute. Yeah.
And I assume you just get to ignore all arrows changing dimension by more than one. Is
Yeah,
that okay?
exactly.
Yeah.
Because
Yeah.
I mean, if you have partial order,
Yeah. Yeah.
Okay. So experiences happened to me. So I'm talking to like experts on quivers. They're very sharp. They're really like legit people I trust. I showed them this quivers and they're like, there's no way. These are not quivers we deal with. So as it turns out, like quiver people usually are more in the mentality of, let me try to classify quivers in which all representations can be sort of expressed. And you get things like thinking diagrams, oriented thinking diagrams, ADE type classifications, and anything that what they call is wild, which in particular is anything like that or anything with too many cycles. They just like, oh, this is, don't look at that. So it was very interesting last year. I had some conversations, and they started to be slightly motivated to look at these diagrams because of that. So actually, even from an algebra perspective, it is not explored at all how to represent these quivers with relations. And sort of the sheaf theory, the symplectic topology says you should expect beautiful answers out of that. Because these things will act as I shouldn't say that. Anyway, these guys, when you take the modelized spaces of these, will act as compactifications of augmentation varieties. And we know they're nice compactifications, so they are related to projective varieties. So even though this looks completely insane from a quiver perspective, actually we know the answer should be very beautiful. So that's maybe a nice first interaction that quiver people could have with us. Are we good so far? Okay. So now I'm going to do exactly the same thing in the last 10 minutes, except I'm going to talk about singular support. And as Hao pointed out, even if I'm going 3 times the speed I should, James in his recitation will go over all of that in extreme care and so on. Okay? So now the question is, if I understand sheaves constructible with respect to each of these 3 certifications, can I actually pin down in linear algebra terms the singular support conditions that are going to tell me that my sheaf is not just constructible, but actually has singular support contained in the Legendre I want. So if I have an arc with a coordination pointing down, I don't want the direction going up to be in the singular support, because that direction going up would be a point in the lift that's not in the Legendre. Does that make sense? I'm trying to translate into linear algebra the conditions that are going to cut out the category SH sub lambda from that category over there. So let's write this very clearly. That was actually a good sentence. So, okay, so proposition. So these appear first in the work of Schendetum and Zattler, like written down. There's an interesting story in there I could tell you about the McPherson Goretzky school to stratified Morse theory. That's kind of where the whole thing came from. McPherson was the advisor of both Nadler and Truman, and Nadler and Truman are 2 of the people who have really pushed this viewpoint. So it all comes together. So this is a description. I like to call this the exodromy description. Exodromy is because it's monodromy, but instead of mono, it's exit path. So exit and monodromy, exodromy. So exodromy description. I didn't make this up. This was the Pine Barwick description of singular supports. This is also something James will talk about in detail. And the idea is, so here, the punchline is how to cut out SH sub lambda of M from the category of SH just constructible sheaves, but with respect to the front stratification. And here via the post-set description. And as I said at the beginning, I'm trying to do in the lectures the simplest possible examples, but I'm stating it in the most general theorems possible, like the exodromy equivalent, such that when you go in higher dimensions or try to do something in research, these lectures are useless in the sense that we know this already, but rather you can use now those theorems in order to prove this. So what are they? Well, say we have this local model in here. So now the orientation is very important. Now it's telling me the only direction that is allowed to be in the singular support. Here. Okay, so this one we've figured out a little bit already. So in this one, if I have these 2 maps in here, the condition is that whatever the stocks are, the condition is that who is an isomorphism, up or down? Down is allowed to be in the singular support, which means this is allowed to be not an isomorphism. So no constraint. There's no commutative constraint. And now I don't want up to be an I don't want up to be a microstock. I don't want the singular support to contain the direction up, which means I don't want sections to go up. But that's exactly what's measured by the downward map. So it is forced to be an isomorphism.
So you say no constraint, but don't you want it to not be an isomorphism? I mean, like what if it was an isomorphism? Then you would lose that singular support, right?
No, but the singular support is contained in lambda. It's not exactly.
Oh, sorry. Okay.
Yeah. Okay.
Gotcha.
So
Yeah.
very good point. Yeah. If I want the singular support to be exactly lambda, then it would have to be not an isomorphism.
I see.
But the constraint is only like
I
the
see.
input.
Mhm.
Like that's why I talked about the empty Legendre, like local systems are always
Yeah,
part of
yeah,
this.
yeah.
Okay, so that's good. Okay, so now let's understand this for a second. So this is equivalent, so data is in fact equivalent to what? Well, if the bottom one is an isomorphism, it means I can invert it. So the data needed in order to specify a sheaf whose singular support is this Legendrian oriented downwards never really had to remember what was on the arc. It sufficed for us to remember what was on the top and what was on the bottom. And now the map that goes from here to the arc can be inverted. Sorry, the map that goes from the arc from here can be inverted, giving you a map from here to the arc. And now the data of this map is equivalent to the data of a map from here to there. So that's equivalent to this piece of data. So you need one map, and there's again no constraint. If the map is not neither, then yeah, you have to say. So when you see me or in talks very quickly, I just say, well, you assign a vector space on this open stratum, and then you do arrows between them. There's 40 minutes of discussion before it, which is no, really the exothermic equivalence tells you this kind of poset. Now, because I want this particular singular support condition, this needs to be an ISO. So I invert this guy. So that's equivalent to the data of a map from here to here. So that's why when we're dealing, for instance, let me start to do an example here, and then James will continue a little bit. So if I had something like that in here, at least away from cusps, and you end up saying something like, I want my sheaf to be 0 outside, and now I'm going to have a representation of dot, 0 outside again here. And now I have one map from here to here, one map from here to here, one map from here to here, one map from here to here. And then it's going to be a map to here, and then 0 map, and these maps off. Does that make sense? So when you draw something of this sort, that's what you're getting. Note that there's also a map from here to here through, maybe I should write it like that, through here and there. Okay, so that's the second condition. So once we have this description near an arc, I know that all I need to care about is the data in here. Well, okay, similar consideration. So I don't have singular support in that direction. That direction tell me I don't need to care about those maps. And now I'm going to have a map going this way and a map going this way. So somehow F, somehow. Does that make sense? So James will maybe elaborate more on that, but given my time constraint, the thing that I will say is that there is a condition for these two maps so that the singular support exactly points up, down, and not any other funny direction in the point, which is the composition of those maps. So F then composed with G, that should be just isomorphic in whichever category you are to the topic to get. Does that make sense? So that's the constraint you're getting at a cusp. And finally, the constraint at a crossing, that's going to be slightly more elaborate, but after similar considerations, you end up understanding that, well, I only need to consider what's on the bottom, on the left, on the right, and on the top. So really, in the end, I only need to consider these 4 vector spaces in here. Let's call them north, south, east, and west. And you can package this data in terms of, so this is now packaged in terms of S has a map, well, 2 maps to E direct sum W, and both of them, by taking the difference map into the north stalk. So you can think about this, the constraint of the singular support being exactly these directions, and in this point exactly being this direction and this direction. So for instance, you do not want the bottom direction or the north direction or east or west to be the singular support, is that if and only if, so you get this singular support, if and only if this complex is a sigma. And this is a condition where it can be phrased in terms of a cone, which essentially you want some microstock to be 0. Microstock is a cone, something being 0 is something being an ISO, that's equivalent to some simplicity condition. And mind you, if I was doing this in DG categories or more general setting, if each of those was not just a vector space, but a complex of vector space, it still makes sense to say it's a cyclic. You just take a total complex of the bicomplex and then that one should be a cyclic. So that's the condition for singular support. What does it mean in real life? And starting tomorrow, already James will discuss this a little bit, is now you're thinking about the trefoil. You have these 4 points over here. For instance, it says, I could take a sheaf which is 0 here, k here, k here, k squared there, and here k just mean a one-dimensional vector space, one-dimensional vector space. What is the condition over here in this crossing? Well, the complex that I get here is 0, k, k, and then this maps into k squared. This map is either 0 or a line. So think of this as maybe being a line. This, you choose it to be a line. Now, question, this complex, understood as a complex, when is it a cyclic? Well, if you have 0 in there, it is a cyclic even only if this direct sum under both maps is isomorphic into this. So this is cyclic, even only if this happens. And that's even only if this splits, meaning this is a direct sum of that. That's even only if the two lines are different. So one way to think about these spaces will start to look like, at least for positive braves, like I choose a line in K2, I choose another line in K2, I choose another one in K2, I choose another line in K2. Here I go from K2 to K. I can think about the kernel of this map, so that's another line. So there's like 5 lines in here. This crossing condition tells me these first 2 lines are different. The second, these 2 lines are different. The third, these 2 lines are different. The cusp condition from here to here will tell you that this line should not project to 0 on this line. So the kernel of these should be different than this line. So now you have a tuple of 5 lines, each of which is different from the next one. And now the subtlety, which is just life, you shouldn't say K2, you should say a vector space of dimension 2. When you do the identification with K2, you're choosing an element of change of basis, so GL2 or PGL2 if you want. So you need to take spaces made of 5, a cyclic tuple of 5 lines, consecutively different, modulo the action of GL2 by you just applying a matrix to each line, the diagonal action. And that's an interesting space. Starting tomorrow, I will start to describe those spaces for you, but that's how you start to connect to things that are linear algebra-ish. Lines and planes and transversality conditions that now it looks very devoid of sheaf theory, but that's exactly what these things are captured. Well, I hope this lecture on this helped the transition from the abstract sheaf theory to a rather more concrete through legal means, like I told you the main box that you need to understand to make these planes really be backed up. And then after the lecture today, which is going to be a bit more about structural results, tomorrow it's really going to be very computational and down to earth and trying to say things through these lines. All right. Okay, well, thanks a lot.